Okay, so I'm presenting today a distributed consistent semantic multi-robot localization and mapping. I'm, as I said, Vladimir Tchuiev, and I'm doing this with the supervision of Professor Vadim Indelman from the Technion. So some introduction for what I'm doing. I'm presenting here an approach for multi-robot semantic simultaneous localization and mapping, or SLAM. This corresponds to perception of the environment, of possibly a vehicle, or in our case, a group of vehicles that cooperates together. So continuing from this, classification is a key component for object-based SLAM. And we have a few key challenges that we have to address. First of all is consistent estimation. I will go over it later what it means. And classification aliasing, that means we observe an object from some viewpoints. From some viewpoints, we can't discern what class the object is. So I will go over our contribution. We first of all maintain this multimodal approach that first of all maintains a hybrid belief over robot and object poses and object classes, compared to previous works that mostly deal with only object poses, robot and object poses. And we address the coupling between classification and SLAM problem via a viewpoint-dependent classifier model. That the works that do address with both poses and classes, they decouple these problems to make it simpler. And also we address estimation consistency for both continuous and discrete random variables, and compared to previous work that they mostly deal with continuous variables. First of all, I'll go over double counting. In distributed system in a multi-robot setting, a measurement should be counted for each robot no more than once. Otherwise, what it can lead to overconfident estimation with a covariance that is too small, or erroneous estimation. And we risk running the problem when we have related information from one robot to the other. I can show you a simple example for that. We have two data sets, in which here Z2 is the shared data set, and we want to compute the posterior. Then we have to if the data is not removed once, like you can see in the red denominator, then the data is double counted. Specifically for discrete random variables, double counting pushes the probabilities, this is a probability vector, to extremes, as you can see here in the illustration, simple illustration that presents what I want to show here. With A, I have a measurement counted once, with B twice, and C 3 times. You can see that in C, the probability is close to 1, 0, 0, 0. The scenario that I present here is shown on the figure on the top right, which we have multiple robots. We're looking at multiple objects. These objects are stationary. Each object has its own bounding box, and from this we have a classification scores. We assume in this setting that our data association is solved, and we use a Gaussian model. This is a standard assumption for a SLAM problem. In which we have a motion model we denote as M, and a likelihood and a measurement likelihood we denote as N. This measurement likelihood consists of geometric model for geometric measurements and a classifier model for discrete measurements. And specifically, the classifier model attempts to predict the class probability vectors that we get from different viewpoints. Our general approach is as follows. We split our combined belief, this is a hybrid belief of poses and classes, into a conditional continuous belief and discrete weights. We do this for a single robot and distributed robot, and we update each one of them. For single robot, we update from the previous prior with the likelihood model and the motion model, and the discrete weight, we do this by integrating over all the poses and using also the previous continuous belief. In distributed setting, we have a similar approach, but this time we also add an update, we also add an update term both for discrete and continuous for each one of the beliefs, both to continuous and discrete. And now, how do the robot communicate between each other? First of all, each robot performs both individual and joint belief inference. It has to do. We have to do this like this to avoid avoid double counting. And each robot maintains a stack of individual hybrid beliefs from stacks that it gets from other robots. The robots send between them the stacks, and each of the stacks contains cells, and each of the cells contain the following variables. We have the marginal object poses, which I denote here as psi. We have the marginal object classes denoted as phi, and we have a timestamp k. Now, how do I update it? Per each cell, if some robot receives measurement, it compares with each cell. It compares the time step between what it has and what it got. If it got a newer time cell, it will update with the following manner that you can see here with this fraction, and the denominator is responsible for removing the previous information, such that we avoid double counting like that. I wanted to present here a small experiment that we did. We have a scenario of 3 robots that communicate between each other, 6 chairs within the environment, 3 candidate classes, and we have a trained classifier model for each candidate class. We compare between 3 cases. Single robot in white will be actually in black, distributing the blue in with double counting in red, and we use for classification a metric that's called MSDE, mean square distance error. Okay, so first of all, I'm presenting here the results for which, if every single robot does its own inference, it doesn't communicate. You can see here that well, I wanted to show the notations, but on the middle, you can see the estimation results. Each object has its own estimation plus ellipse, covariance ellipse. And on the bottom, you can see classification results. Basically, the ground truth is that everything is blue. It represents class number 1, which is a chair, and I want the ground truth to be everything like a chair. Now, for distributed systems, I want to show here, first of all, that the coverage is larger than the single robot case, and also the classification is more accurate. In the previous case, the classification was erroneous for one of the object for the middle robot, but now with the shared information, you can see that the error actually, the robots communicate, and using that we correct this error. We have here the robot estimation metric that we compare between the cases no communication, distributed, double counting. You can see that generally distributed performs the best here. And 1 second. Here you can see the covariance, the estimation covariance. This is the covariance, the square root of the determinant. And you can see that, as expected, the covariance is largest for no communication, and double counting is actually the smallest, but it is an overconfident estimation. And if I go here to mean square detection error, you can see that eventually distributed case performs here the best of all of them. This is closest to 0 after all the time steps. So when I go back here, I want to go over the summary, and well, I will go over quickly. So excuse me if the split screen is not working correctly. I presented here approach for multi-robot semantic SLAM. That maintains a hybrid belief over both robot and object poses and object classes. We address the coupling between classification and the poses via viewpoint-dependent classifier model, and we avoided double counting both in continuous and discrete random variable. And that's it. Thanks.